Um, Hello everyone. So in this slide, in this video, we will talk about confidence intervals and hypothesis testing for mu and sigma square. Again, but this time we will talk about one-sided tests. Okay, one-sided tests. So what does this mean? So up to now, we just deal with this type of hypothesis testing. Okay, we just check whether mu is equal to 5 versus mu is not equal to 5. Okay, so in fact, recall an example where we just test the lifetime of people. Remember, there were 100 many people. We just check whether mu is equal to 70. So the average lifetime is equal to 70. Remember that question. Versus mu is not equal to 70. Okay, we just test whether the average lifetime of people in Turkey is equal to 70 or not. And we just check lifetime of 100 many people, and it turns out that X bar was equal to what? Remember 71.8, right? So we just make this test. So in fact, what we did was, well, so just look at this one, 71.8. So let me ask you this question. If X bar was exactly equal to 70.0, will you make this test? Right? Will you test whether mu is equal to 70 versus mu is not equal to 70? Well, we won't make this test. Why? Because we just make the tests whenever the data that we have just favors the alternative one, or there is an evidence which says that in fact mu is not equal to 70. Okay, so here the evidence says that, well, mu is equal to 70. So the only data that we have says that the average lifetime of people is 70. So there is no other thing that makes us believe that the average lifetime of people in Turkey is not equal to 70. There is nothing that makes us to believe that mu is not equal to 70. Okay, hence, if x bar is exactly equal to 70, then there is no need to test, let's say, mu is equal to 70 or not, right? There's no need to test this. However, remember the question. The question says that x bar is equal to 71.8, which says, well, I say mu is equal to 70. So the real data says that, well, it's not exactly equal to 70, but it's something different than that. So what I do is I just make the test, and to see whether, let me say, whether this evidence, in fact, let me just write this. So here we make the test, okay, to see that, what? To see, right? Whether the evidence, what is the evidence? Evidence is x bar is equal to 71.8, okay? Is sufficient, or is statistically sufficient, right? To show that mu is not equal to 70, right? So our aim is to see whether this evidence is sufficient to show that mu is in fact not equal to 70, right? So this is what we did so far. This is what we call a two-sided test, okay? Two-sided test. Now we also have one-sided tests, like what? We may have something like this, okay? We may have, okay, let's say mu is equal to 5 versus mu is greater than 5, or mu is smaller than 5 versus mu is greater than 5, okay? So in fact, instead of null hypothesis, when we just use a single-sided test like this, we may use both of them. We may just write both of them. There is no change in terms of performing the test. So there is no difference in the whole process of the test. But in representation, you may just write mu is smaller than or equal to 5, or mu is equal to 5. Okay, there is no change in this. So we may have this kind of test, or we may have mu is greater than 5 versus mu is smaller than 5, okay? So again, here you may just write mu is equal to 5 versus mu is smaller than 5, okay? So these tests are called one-sided tests. Okay? One-sided tests. So, um, so in general, we use the alternative hypothesis to justify our beliefs. So what does this mean? So for example, if you believe that the real mean is greater than 70, what you do is you just put this into the alternative one, okay? Or for example, if you believe that, for example, the GPA of the male students, okay, is greater than, again, the GPA of the females, right? What you do is you just put this into the alternative one, right? Why? Because it turns out that you have an evidence for this, or it turns out that you have an evidence for this. And so what you want to do is you want to prove this. How to prove this? So you want to show that your evidence is statistically sufficient so that the alternative hypothesis is true. Okay? So we just want to test whether the evidence is sufficient to suspect the null hypothesis, and you want to prove the alternative one. Okay. So, right, now let's make the example, the very, very same example. A random sample of 100 recorded deaths in Turkey. It turns out that, well, 71.8 years. Okay. So I want to test the following hypothesis. So test whether mu is smaller than or equal to 70 again. So this is equivalent to mu is equal to 70 versus mu is greater than 70. Okay. So in fact, the real notation is this. Okay. The real notation is this. However, remember, when you apply the hypothesis test, you say that we just apply the hypothesis test by assuming that H0 is true, okay? So assuming H0 is true when mu is smaller than or equal to 70, then it is hard to just find the value of mu to use in z observed, for example, right? Z observed is equal to x bar observed, let's say, minus mu divided by sigma divided by root n. So what is mu if h0 is true and if you just use mu smaller than or equal to 70? Okay? Hence, how we show we have an equivalent representation for this hypothesis testing, which is mu is equal to 70 versus mu is greater than 70. Okay, then assuming h0 is true, when we have this kind of representation is easy. Then we just put mu is equal to 70 there, right? But as I said, so both of the representations are equivalent to each other. You just test the same thing. There is no change in just performing the test. What you do is you just put this number, okay, this number as your let's say as your mu when you are calculating the observed test statistics. Okay, so, well, this is my test. I want to test this. I want to test whether mu is smaller than or equal to 70 versus mu is greater than 70, right? So what is the catch here? Well, I have an evidence x bar 71.8, which is clearly greater than 70, okay? So I want to test whether this is sufficient, okay? So this evidence is sufficient enough to show that, well, the real mean is really greater than 70. So this is, well, 71.8 is greater than 70. So why do we make a test? Okay, so this is my critical question in many exams, and especially in, for example, in PhD qualifiers. So that's because, well, x bar is the sample mean. Okay, so this is the mean of the sample. What I'm trying to do is, by just looking at the sample mean, I want to say something about the real mean, okay? So 71.8 is greater than 70. Well, is this evidence sufficient enough to say that mu is in fact greater than 70 or not? Okay, so this is our main thing here to do. Okay, so assuming that sigma is equal to 9, please just make your hypothesis testing with 0.05 level of significance. So, well, we know sigma, hence we can just use z here. So we have a single sided test. Hence, we have a rejection type. So remember, our when we have alpha, and if we just use z as our test statistic, okay, what we do is you have here I have alpha over 2, okay, and here I have alpha over 2, okay. So this is a one-sided test. So since this is, so what kind of a one-sided test? We just test whether mu is greater than or greater than 70 or not. Okay, so now our test is mu is greater than 70, which means, well, I have a rejection region of type like this. Okay, so I don't put anything here. Okay, there is no region here because this is a single-sided test. Well, I just put all of my alpha. Okay, so this is what this is alpha. Okay, so be careful. This is not alpha over 2. Okay, this is not alpha over 2 because now my extreme points are on one side. It's not on two sides. So my extreme points are on one side. So these are my extreme points. Well, the area here is alpha. Okay, so this is my rejection region. Okay, so since alpha is equal to 0.05, well, this area here is, let's say this is alpha, which is equal to 0.05. Hence, this is what? This is z sub 0.05, okay? Which is equal to 1.645. Well, what is z observed? Let's calculate the z observed. 71.8 minus 70 divided by 9 divided, well, 9 over 10, which this is, remember, this is square root of 100, okay? So this is equal to square root of 100. That's equal to what? That's equal to 2, right? 1.8 divided by 0.9. And 2 is, let's look at here. Let me just change the color here to just, no, it's a bad one. This is orange. So it's somewhere here. Okay, it's somewhere here. 2. This is what? This is z observed. This is z observed. Okay, which is equal to 2. It's in the rejection region, right? It's in the rejection region. Hence, we just reject H0. So in fact, so if we just go back to the our stepwise procedure for hypothesis testing, everything remains the same. Step 1, what is your hypothesis test? That H0 mu is smaller than 70 versus mu is greater than 70, okay? 7 smaller than or equal to. So step two, just pick your random variable or test statistic, which is z here. Okay, step 3, find your critical region, which is z. Now this is my critical region is z alpha infinity. Okay, so here expressing the critical region is much more easier than before because I don't need anything like r minus something like that. So in fact, okay, let me just write, this is something that r minus what? R minus infinity and z alpha, okay? But this one is easier, okay? So this one is much more easier. This one is easier. So step 4, calculate your z observed, okay? Z observed. Then step 5, conclude, okay? Conclude. So the same procedure here, exactly the same thing. I just write the null hypothesis. I just pick z, then find the critical region, which is just given here. Okay. Then calculate your z observed, which is here, and just by looking at whether z observed is in the critical region or not, just make your conclusion. Okay. The procedure is complete the same. Now let's talk about the other test, which is just test whether H0 mu is greater than or equal to 70, H1 mu is smaller than or smaller than 70. Okay, how about making this test? Right. Again, just write your step 1, then step 2. Okay, step 3. What is the difference? The difference is in where? The difference is in this critical region, right? Step 3. Then step 4, step 5, and so on and so forth. But before making this, let me just change the color again. Okay. Before getting into this, now please note this thing. Well, what was our X bar? X bar is equal to 71.8. So does it support, so this is an evidence, right? Does it support H1? Okay, so by looking at 71.8, does it support the alternative hypothesis? Well, no. The alternative hypothesis says that mu is smaller than 70, okay? But you have an evidence which says that, well, mu should be greater than or equal to 70. So in fact, it just supports what? It just supports the, the well, the null hypothesis, okay? So in fact, if you have a data which supports the null hypothesis, okay, then there is no need, okay? Then there is no need to make the test, right? Make the test because well, you you cannot reject the null hypothesis because your evidence is already supporting the null hypothesis, okay? So if your evidence, if your observed x bar, if your observed random variable supports the null hypothesis, then there is no need to make the hypothesis test. Okay, so, well, let's look at the steps. In fact, we have already written that. So step one, just write your null hypothesis and alternative one, then calculate your z observed, okay? So this is x bar observed, your observed average minus mu zero, which comes from the null hypothesis. That's why we just say that, well, this is an equivalent form of mu is greater than or equal to mu zero when you're just writing the null hypothesis, okay? Because when you say assume that H3 is true, then it's hard to use this, okay? But it's easy to use this one when you say assume H3 is true. Then step three, well, what is your rejection region or critical region? Okay, so this is my critical region. So how do we understand whether the critical region is on the left or on the right? So just look at this one. This is a smaller than or equal to type of hypothesis test, smaller than or equal to, okay? Mu is smaller than or equal to mu zero. So alternative one says that mu is smaller than or equal to mu zero. Then what you do is, so let me just draw this. This is, okay. So this part, when you have H1, mu is smaller than or equal to mu zero, right? But if you have mu is greater than, then your, let me just plot this, then this should be your critical region. So this is what? This is when H1 says mu is greater than some scalar mu zero, okay? So this is your critical region. Your critical region is equal to what? Z alpha infinity. This is your critical region, right? So in the previous one, your critical region here is minus infinity minus z alpha. Okay, great. Then calculate your z observed. Okay, calculate your z observed. And then if the z observed is in the critical region, which means if z observed is smaller than or equal to minus z alpha in this case, okay, so this is what we are just testing, then we just reject H0. Okay? So this is smaller than, okay, just look at this one. This is smaller than. Now exactly the same steps for greater than, okay, for greater than. Now the test statistic is the same, z observed, but now the critical region changes. It's z alpha to infinity. So this is something like this, sort of for the square brackets. So calculate the z observed using this one. And then if z observed is greater than z alpha, which means if it is in the critical region, okay, then we just reject H0. Okay, that's great. Well, the next step is, of course, so up to now, we deal with the cases where, just let me just go back. We just deal the cases with when sigma is known, okay? Hence, we were able to use Z, right? We were able to use Z. Now, we will talk about cases where sigma is unknown. So we have exactly the same situation for mu is greater than or mu is smaller than. The only difference, what? The only difference, as you might guess, well, it's in the calculating the test statistic, using the test statistic. Now, instead of z observed or instead of z, we just use what? We just use t, okay? So this is x bar minus mu 0 divided by s divided by root 10. Remember this? So it was sigma in previous slides, okay, in previous slides, right? Okay, then T alpha to infinity, just calculate T observed using step 2, and if T observed is in the critical region, we just reject the H0. And the same procedure if mu is smaller than, okay? So again, I have two types of test here, mu is greater than and mu is smaller than, okay? And we just calculate the rejection region by just looking at this, right? And just go back. Okay, this is greater than, hence my rejection region is T alpha to infinity. This is smaller than, hence my rejection region is minus infinity to minus T alpha. Okay, and the whole procedure is the same. Well, all other hypothesis tests can be just made using similar arguments. Okay, you can just check the two means, the single variance, which we will make in a minute, and two variances cases. So let's make an example here. For first, we'll deal with the case where we know sigma. Okay, a manufacturer of sports equipment has developed a new synthetic fishing line. Okay, and they claim that this new synthetic has a mean breaking length of at least, let's say, 8 kilograms. So this fishing line has a mean breaking strength of 8 kilograms and with a standard deviation of 0.5 kilograms. So a wholesale store, just like Decathlon, is interested in this synthetic fishing line, but before they can advertise this claim, so before they can just put this info to their website or to their catalog, so they just want to make a test for this. So if the new synthetic lines are weaker than 8 kilograms, they won't buy it. So they are planning to buy from this fishing line in huge amounts. But if the new synthetic lines are weaker than 8 kilograms, they won't buy it. Otherwise, they will just buy in large quantities and make the, let's say, make the advertisement of them. So they want to test whether mu is greater than 8 versus mu is smaller than 8. Okay, so they want to show, in fact, this, that's why we just put this into the alternative hypothesis. But as I said, so in a question, not most of the time, every time you will understand what you should just put to the alternative hypothesis. Okay, so for example, the question says, well, Mehmet Hoca thinks that the average height is greater than 180 centimeters, or for example, Erin Hoca thinks that the GPA of the male students are greater than female students. For this kind of tests, what you will do is, for example, for the first one, mu is greater than 180. For the second one, mu of males is greater than mu of females. So this should be your H1. So what you are planning to do is, what you want to show should be put into the alternative hypothesis. Why? Because you have a data, okay, you have a data which supports the alternative hypothesis. Otherwise, you won't make any test. So here, well, so the people there thinks that, well, the mu is not is smaller than 8, so they want to just make this test, okay? So they just take 50 many lines, fishing lines, and it turns out that X bar is equal to 8.75 kilograms, okay? So I want to make this test, right? So again, remember, this is equivalent of testing mu is smaller than or equal to 8. Sorry, this is not true. This is not true. So, okay, let me just erase this part. Um, So I want to test whether mu is greater than or equal to 8 versus mu is smaller than 8. Okay, so these are not true here. Okay, so I just made a little change in the slides. So the question asks the result for alpha equal to 0.01. okay? And I just changed the hypothesis. So I want to test whether mu is equal to 8 or mu is greater than or equal to 8 versus mu is smaller than 8. Why? So if you reject the hypothesis, if H0 is rejected, right? If H0 is rejected, then you won't buy them, okay? You won't buy them. If you cannot reject them, you won't buy them. If it is not rejected, then you will purchase in greater quantities. So, well, for z sub 001, it turns out that the value is equal to minus 2.33. And, well, remember, this is my test statistic, x bar minus mu 0 divided by sigma root 10. So what is my z observed? Just put the values there. 7.85 minus 8, right? This comes from the null hypothesis. Remember H0. Sigma is 0.5. Assume that it's true. In the next question, we will assume that we don't know sigma and just use S, the sample standard deviation. But for now, I'm just using sigma there. And it turns out that, well, z observed is minus 2.12, okay? And this is not smaller than 2.33, which means, well, we cannot reject H0. We cannot say that, well, the average strength is smaller than or equal to 2 point, the average strength is smaller than n. Hence, the company will just consider buying the fishing lines, which means there is no enough evidence that the strength of the fishing line is less than 8 kilograms, okay? So assume, well, we are not given sigma, okay? And I just want to use the sample standard deviation, which is 0.84, 48, sorry. So the same question for alpha 0.01, okay? Now I just need the t value, the t sub 001, okay, which is, so this is minus. So this is minus t, okay, minus t sub 0.01. This is minus 2.40. Remember, it is very close to the normal value, which is minus 2.33. So the t has a 49 degrees of freedom because we have 50 observations, okay? So we will reject hypothesis. This is not greater than, but this is smaller than or equal to, or smaller than. We just reject hypothesis if it is smaller than this. Well, the T observed is equal to minus 2.21, okay? Which is, okay, let me just, this is not true. Let me erase this. So minus 2.21 is not smaller than minus 2.40. Hence, we cannot reject H0, okay? Okay, I've just corrected this, right? So, right? So if t is smaller than minus t sub 001, which is minus 2.40, we will reject the hypothesis, but, well, it's not, okay? So it's not smaller than or equal to or smaller than minus 2.40, and we cannot reject H0. Now, please, we will see that again. The hypothesis testing is equivalent to confidence interval. So, well, we will make a two-sided alternative, okay? We want to make a test where mu is equal to 8 versus mu is not equal to 8 at a significance level of alpha that's equal to 0.02, okay? Well, if you are making the hypothesis test for alpha is equal to 0.02, then you will reject the hypothesis if your observed, so this is, let's say, t observed is greater than 2 t sub 001, or if your t observed is smaller than minus t sub 0.01. Okay? So since your t observed, which is this, is greater than minus 2.40, or since it is not smaller than minus 2.40, we cannot reject H0 at this time. Okay, so in fact, this is exactly the same solution, let's say, values that we have found in the previous slide. Now for the confidence interval, let's write a 98% confidence interval for mu, x bar minus t alpha over 2 times s over root 10, and in the right part, I have a plus here. If you just plug in the values, this is your x bar, this is your t alpha, This is your S, okay, S value, and this is your root n. That's equal to 7.69 and 8.01, okay? So see that, well, S is an element, 8 is an element of 7.69 and 8.01. Hence, we cannot reject H0, okay? So for example, if I just ask you, just test whether mu is equal to 7.8 versus mu is not equal to 7.8, right? At the same alpha level, at alpha is equal to 0.02. So what should be your answer? Well, since 7.8, since it is in the confidence interval, I cannot reject it, okay? You cannot reject this, right? Okay. So now let's talk about one-sided tests for variances. So okay, so one-sided test for sigma. Well, first, so we know this part, okay? We know this part, how to test whether sigma is equal to this thing or not equal to that sigma 0, okay? Uh, Okay, now we will concentrate on whether sigma square is greater than sigma 0 square or sigma square smaller than sigma 0 square, okay? So remember, this is equivalent to testing H0 sigma square is smaller than or equal to sigma 0 square, and this is equivalent to sigma square greater than or equal to sigma 0 square, right? But as we said, since I can just write this in terms of equality, we can just write these things, okay? Well, of course, your test statistic is chi-square with n minus 1 degrees of freedom. And the next step is find your critical region, okay, for chi-square. How to find the critical region? How to find the critical region? We will deal with this. We will deal with this. Then calculate your chi-square observed, right? And finally, draw the appropriate conclusion. If chi-square is in the critical region, okay, if chi-square observed is in the critical region, then reject, okay? Then reject H0, reject H0. So how to find the critical region? Well, for this one, we know the critical region, okay? For this one, we know the critical region. For example, let's talk about, okay, let me just divide this part into two, okay? So this is the chi-square random variable. So for the case where you have h1 sigma square is greater than sigma 0 square, then since this is a greater than, you have the right hand side, okay? So this is your alpha, okay? This is your alpha, and this is your chi-square alpha. But if your h1 is of this type, sigma square is smaller than sigma 0 square, okay? Then you have what? You have alpha here, okay? Alpha this part. So this is alpha, and this is chi-square 1 minus alpha. Okay, so this is your critical region. So what is the critical region here? It's chi-square alpha infinity, and here minus infinity chi-square 1 minus alpha. Okay, this is your critical region. Right, for example, for the greater case, so we have exactly the same thing. For the greater case, this is my critical region. Okay? So let's make an example and finish our one-sided test for sigma. Well, a manufacturer of car batteries, just like in JAQ, claims that the life of the company's batteries is approximately normally distributed with a standard deviation of at most 0.9 years. So the test, if the standard deviation can actually be larger than this claimed value, a random sample of 10 of these batteries is selected and tested. The sample standard deviation is found to be 1.2 years. Okay, so what I'm testing is H0. whether sigma is, let's say, smaller than or equal to 0.9 versus H1 sigma is greater than, sorry, greater than, not greater than or equal to 0.9. Again, why? Why? Because this evidence supports the alternative hypothesis, okay? So if the value here is not 1.2, but if it is 0.5, then there is no need to make test because there is no evidence which supports the alternative hypothesis, okay? Well, do the data support the manufacturer's claim? Let's try to see this. Use a 0.05 level of significance. Well, I will just make this. So remember, this is equivalent to, well, this is equivalent to sigma is equal to 0.9, right? Because this is sigma squared. I just take the square of this versus sigma squared is greater than sigma is greater than 0.9, okay? So for 0.05, well, the chi-square, the critical chi-square value is 16.919, okay, with 9 degrees of freedom. You can just check it from the table. Okay, so let's look at the chi-square table. So I have the 0.05 values of alpha here, and the degrees of freedom is 9 here. Okay, this is 9, right? And the corresponding value is, let's just see, 16.919. So what does this mean? What does this mean? 16.919 at alpha 0.05 and at degrees of freedom 9. So what does this mean? So in terms of probability, just make a recall first. The probability that chi-square random variable with v is equal to 9 degrees of freedom, the probability that this is greater than 16.919, that's equal to what? That's equal to 0.05, okay? So this is the chi-square value. So this is 0. Let's say this is the chi-square plot. Right? So this is what? This is 0.05, 0.05. And the value here is the chi-square value is equal to 16.919. So this is the chi-square sub 0.05. Okay. Now let's calculate the chi-square observed. Chi-square observed. Chi-square observed is, this is what? This is sigma, okay? This is 1.44, which is s square. Sorry, this is n minus 1. Sorry, this is n minus 1, okay? This is s square, and this is what? This is sigma square. Chi-square observed is 16. So 16, well, is not significant because it's not greater than, so what was our original value? 16.919, okay? So it's not greater than 16.919. Hence, well, the chi-square statistic is not significant. Hence, we cannot reject H0, okay? We will also see the p-value, but later, it's not here, okay? Great.